Hey there everyone, welcome back. So this video will be all about collisions, all right? So in this chapter, we really have two general types of collisions, but you'll see that they can be further broken up into really three specific types of collisions. The first type is elastic, okay? So that's not necessarily like elasticity like a rubber band, right? Elastic in this case means there is zero deformation, or in other words, zero energy lost when particles collide. Okay? So what we have here is a red ball, right, of mass m1 and speed 5 meters per second. And we'll actually call this the initial speed, okay, because it's pre-collision. Mass 2 is not moving, right? But M1, if we say that has a mass, well, actually, let's hold off on numbers for right now. Sorry. All right. So if mass 1 is moving and mass 2 is not, what's going to happen? Well, if they elastically collide without any deformation, that means that when they're in contact, so right there, there's an equal force of mass 1 on mass 2 and mass 2 on mass 1. There's equal and opposite forces, right? Newton's third law. And because of that, and because of the impulse momentum theorem, the momentum initially, so just mv of that one, because the momentum 2 is 0, this momentum has to equal the momentum after the collision, whatever that is, and however that's split up between the two particles. So we write that very simply as P initial equals P final. And I guess I should put the vector bars on top, right? And this is conservation of linear momentum. And it straightforwardly comes from Newton's third law, right? There's always an equal and opposite reaction force between two particles when they collide. And this is true regardless of what type of collision happens. All right. So in the case here, let's be very explicit. M1 V1, this is initial, plus M2 V2 initial has to equal the same thing final. So M1 V1 final plus M2 V2 final, right? This whole thing is the conservation of linear momentum, right, for an elastic collision. Notice there's 4 terms, right? There's a pair, initial and final, for each object. It just so happens that in this case, initially mass 2 is 0, right? But other problems may be different, right? This is just the conservation equation for an elastic collision. So I guess I should write up here elastic, right? And so this means no energy. Actually, let me put that. That was a silly place to put that. Let me put it here. No energy is lost, right? And that also means that the objects do not deform. So no deformation. Places where the energy could go is to, if they did deform, the objects would heat up a little bit, right? But we'll talk about that momentarily with inelastic collisions. So the other conservation equation, in addition to linear momentum, is the conservation of kinetic energy. So we'll write that as K initial and K final. Okay? So for this, right, the form of kinetic energy is 1/2 m v squared. So I've written that as 1/2 m1 times v1 initial squared. And we have to do this for every term. So 1/2 m, 2 V2 initial squared. And the same thing after the collision. So 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. All right. So again, we have two conservation equations for elastic collisions. Both linear momentum and kinetic energy are conserved. Now, let's go over to inelastic collisions. All right, so inelastic. And this is the type that can really be broken up into two subtypes, if you will. So the picture I have here is two train cars. Right? Car 2 is in blue, car 1 is in red. Let's see, car 1 is less massive than car 2, but car 2 is traveling faster than car 1. They're both traveling in the same direction, so that means that eventually car 2 will catch up to car 1 and bump into it. Right? And so what we've drawn here is that the connection point, once they bump, they stay connected. So then they effectively move as one whole train car, right? So their masses are effectively added up. However, this is an inelastic collision because they do not bounce apart, right? They stick together. In the previous example, elastic collision, I don't have a picture of after, but once this red ball moved into and collided with mass 2, they would bounce apart, right? And they would not stick, nor would they deform shape. Here, they stick together. And so you still have conservation of linear momentum, right? Because there's still a force during the collision. So thus, Newton's third law still applies. So linear momentum conservation always occurs, right? But we can write it like this. M1 V1 initial plus M2 V2 initial, right? That part is unchanged. It's the final that switches a little bit. Now, momentum is still in the same form of mass times velocity. Velocity. However, we have a total mass, since they're moving as one object now. And so now we effectively have the total mass times the final velocity. That's it. Okay? Now, because they stick together, that means that kinetic energy is not conserved. Okay? It's not conserved. If you want to check me, plug in these numbers I have here. Right? Plug in these numbers, we can find the final velocity. If you do, we get a final, let me check my notes. We should get a final velocity of 1.09 meters per second, okay, or final speed in this case, rather. And so using that, if you want to plug it into kinetic energy conservation, in other words, into this equation, right, they're not conserved. Specifically, if you want to plug it into this, 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared, and since they're one mass, V final squared, right? If you get a number here, you should see that they're not equal, right? In fact, you'll see that about 5,200 joules of energy are lost, right? You'll see that 5,200 joules of energy are lost. That's a considerable amount, right? Initially, let me go ahead and plug in the numbers I got. 98,540 and then 93,266. Okay, so where does that energy go? Well, it goes into the connection, right? It goes into slowing down mass 1 and speeding up mass 2, but at the same time, if they were to elastically bounce apart, they're still connected, so that prevents them from moving apart, and so that takes a little bit of the energy, right? It's really in the minutia of the connection, right? But when objects stick together, whether they're two train cars, whether they're I don't know, a ball of peanut butter and your brother's face, I don't know, whatever they are, kinetic energy is not conserved. Okay, it's just not. The other type is when they do stick together, but they deform their shape, right? For instance, two tennis balls colliding together. When they collide, two tennis balls, well, before they'll look like, spheres, like that. But after, they'll look something like this. Oops. They'll look, something like that, deformed circular shape, right? So there's still two balls, 1 and 2, but now they're colliding and they've deformed their shape. So that energy that's lost has gone into into heating up the molecules of the rubber, right? And so it's heat loss to the environment, and that cannot be put back into those two particles. Okay, so two instances of inelastic collisions, right? One, when objects collide and stick together, and two, when they collide and deform shape, but then they move apart. Okay, they don't stick together, but they deform shape. In both cases, kinetic energy is not conserved, but linear momentum is conserved. Okay, so keep this in mind when doing these collision problems, right? This is very, very important. Okay, so with that, thanks for watching.